Hello, everyone. So within this subject, mechanism machine, so in continuation of, so we have some of the glossary which I thought is important to introduce in the beginning of our lectures. Uh, so that's why I have one of the fundamental definitions, which will be quite useful. So I have tried including those here. So we'll go one by one. So we start with kinematics. You might have used this during the static and dynamic study. So kinematics is the study of motion. So when we call motion, so it means it could be position, velocity, acceleration. So in motion, it could be anything. So a major goal of understanding kinematics is to develop the ability to design a system that will satisfy specified motion requirement, right? So the main goal is revolves around just the motion understanding of the system. But when it comes to kinetics, so the effect of forces on moving bodies. So you see here, the additional thing is the force, which is acting on a moving body. So kinetics is a one step ahead of kinematics. So in kinematics, we just do the motion, so mean moving body. But here in kinetics, we see the effect of forces on the moving body as well. And in kinematics, we were not concerned about the forces. So that's the major difference. That was one of the good statement. So it's a good kinematic design should produce good kinetics as well. So you start with the kinematic. So if you have a good design of kinematics, so you will certainly have good kinetics as well. Mechanism. Again, we will use quite a lot this word. So the mechanism means a system designed to transmit motion. Uh, the only thing is here is it is more like a low forces are in consideration. But when we say the word machine, a system designed to transmit motion energy and forces involved. So you see mechanism and machine both are dealing with the motion. So transmitting motion, when we say transmitting motion means from input to output. So it transmits motion. So the purpose of mechanism to transmit motion from input to output, and machine is also doing same thing, but in addition to that there is a energy involvement and the forces are involved. There might be some low forces are involved in this one, but you know there are few things you need to consider. That is basically a mechanism or a machine. They are more widely uh, reported reported definition. So it could vary from book to book. So the one I have listed in this lecture is are more fundamental to make it simpler definition basically. So the basic mechanism that includes, for example, gear system, cam follower system, and linkages. So rigid link connected by sliding or rotating joints. So we will study about joints in this lecture as well. So we'll go through one by one later on. So a mechanism has multiple moving parts. For example, a simple hinged door does not qualify as a mechanism. Just make sure you follow this. So the mechanism has multiple parts. So it's not like simple part relatively. Um, all right, so the next is degree of freedom. Uh, I'm quite sure you would have used this word quite frequently. So it's just a little bit of further explanation here. So the number of inputs required to completely control a system. So if there is a system, you want to explain it or define it, the number of that defined inputs will give us the degree of freedom. Uh, for example, a simple rotating link, a two link system, a 4-bar linkage, a 5-bar linkage. So these are basically the example of mechanism, right? Uh, so we have the types of motion. So mechanism may produce motions that are pure rotation. So it really depends. So this classification is based on the uh, motion basically. So for example, there is any mechanism which can only rotate, or a mechanism which can purely translate, or it could be combination of two. So certainly it is basically depends on the classification, I would say. Um there are very broad understanding. So it's not necessary that this is a particular classification. This is just the types of motion. Sorry. Yeah. So this is just based on the motion type actually. So for example, pure rotation, pure translation, or combination of two. So we reduce the degree of freedom of a mechanism by restraining the ability of the mechanism to move in translation, which will be called as XY direction for a 2D mechanism, or in rotation. Yeah. So this relative movement we will discuss in a while. So interactive slides, which I will show the proper mechanism depending on the type of motion. All right, so a few more further definitions. So for example, link. So we will use quite a lot link, the word link. So what is link? Link is basically um yeah. So the link is a rigid body with two or more nodes, right? And those nodes are called as a joint as well. So the purpose of link basically to connect. So it is a rigid body. So I assume you know the rigid body. I have definition also in the just a revision, but generally the rigid body is the one which does not have any deformation between relative points, arbitrary points within the structure. So a rigid body with two or more nodes that are used to connect to other rigid body. So the examples are binary link, ternary link. There are three joints and there are four joints in quaternary link. So these really depends on how many joints are being possible. I think I have. Let me show you one of the example here. Yeah. So this is one of the slider crank mechanism. So how it is working basically. So this is represent. So this is slider crank mechanism, which is basically a piston, connecting rod, and crankshaft assembly. So for example, this is analogous to piston, this is connecting rod, and this is crankshaft. So when it's rotating, so it is reciprocating. So that's why it's called as a slider crank mechanism. So for example, now if you see carefully, so this three is called as a link. It's a one link. So here 1, 2, 3, 4. There are four different links. So three is a link. So each end of the link is connected with other link. For example, 3 and 4 are connected together through a joint. This is called as a joint. And 3 and 2 is also connected through each other. That's also called joint, or you can call it as a node as well. So there are two different terminologies. So here I will just go back and come back here again. So what is link with context to the slider crank mechanism you have seen? So again, a rigid body with two or more nodes that are used to connect to other rigid bodies. So you see the link is basically uh, is connected through the nodes or joints. And what is joint now? A connection between two links that allows motion between links. Yeah. So there are two links that allows motion between links. So you have seen slider crank mechanism. So each end of the link was a joint. So at joint, there is a motion. So there is a relative motion at particular joint. So the motion allowed may be rotational, which is called as a revolute joint, translational, which is called as a sliding or prismatic or prism joint, or a combination of two, which is normally called as a roll slide. We will study today a further classification of these joints in a while. And then there is another definition called as a kinematic chain. So an assembly of links and joints used to coordinate an output motion with an input motion. So it is assembly of links. So we have explained link, we have explained joint. The kinematic chain is the assembly of links. So in a slider crank mechanism, I will go back again. So within slider crank, so this is kinematic chain where assembly of links are available. What does it mean? So 2 is a link, 3 is a link, 4 is a link, 5 is a link. So they are connected with each other at further joints. So that's what we call as a kinematic chain, basically. All right. Then we have a link or element. So a mechanism is made of number of resistant bodies, out of which some may have motions relative to other. So a resistant body or a group of resistant body with rigid connections preventing their relative movement is known as link. So it's a little bit of different way of explaining the link. That's another definition of the link. So what it says, a mechanism is made of number of resistant bodies, out of which some may have motions relative to others. So a resistance body or a group of resistance body with rigid connections preventing their. So it is again, the definition is a rigid link. So there is no deformation between the within the link. That's important actually. So a link may also be defined as a member or a combination of members of a mechanism connecting other members having relative to them. Thus, a link may consist of one or more resistant body. A link is also known as kinematic link or an element. Yeah, so the message here actually. So a link not necessarily is a straight line. For example, here, this is very simplified version of a piston internal combustion engine. So slider crank mechanism where connecting rod shown as a one straight line, crankshaft shown as a one straight line, piston shown as a one straight component. But a link could be this one as well. So if I will repeat again. So within link, there is no relative motion. So again, let me explain here. So there is no relative movement or motion between two links together, right? Within the link. So as far as it is designed for, let's say you apply a lot of load, it is plastically deformed. That's another story which is not being considered here. A link has to be rigid. So you see within that link, it will always remain a straight line. So there is no plastic deformation within that link. But here, this is another example of link. So all is one rigid body, but it has four ends. So you can connect four different links here, four different links. So when you connect four different links, so this will still be a one link. Yeah, that's important to understand. So link is not necessary to be just one line or one element or one component. So this is one component, but by the definition of link, it's supposed to be rigid body. This is rigid body, but it is further connected with other parts. So it is still a one link basically. All right. Yeah. So this is the example for kinematic pair. So what is kinematic pair? So kinematic pair or simply pair. Yeah, this is quite common word which is being used in mechanics of machine subject or theory of machine subject. So kinematic pair, or most of the textbooks, they just write it as a pair. So it is a joint of two links having a relative motion. So is a joint of two links having relative motion. So you connect two links together through a joint, of course, because joint is the basically the point where both links are connected. So Kinematic pair or simply pair is a joint of two links having relative motion. So it is necessary for a pair to have a relative motion, right? So in the given slider crank mechanism, link 2 rotates relative to link 1. So you see this is link 2, this is link 1. So yeah, so this is also link 1. So because both are stationary, so that's why being considered as a one link. So link 1 and 2, just imagine when it's rotating in any direction, clockwise or anti-clockwise. So it is called as a link 2 rotates relative to link 1, right? So this is rotating and constitutes a relative revolute or turning pair. So such a combination where one of the link is revoluting or turning with reference to another link is called as a turning pair. All right. So similarly, link 2 and 3. So 2 and 3 and 3 and 4. So 3 and 4 constitute turning pair. Understand again. So what it says, so between 2 and 3. So you just imagine when it's rotating like this. So at this particular joint, you have a turning pair. So basically both links are turning with respect to this joint. And same thing here, 3 to 4. So of course, at this point 2 or at this particular point, they are making full angle. So 360 degrees rotating. But here it will just go up and down, covering some of the angle. Just imagine when it goes straight. So this angle will become 0. And then when it reaches at this particular point, you will have some certain angle, the maximum and minimum angle. So of course, it will not make a 360-degree revolute, but it is still turning pair. So it is still called turning pair. Yeah. All right. So again, it's been explained, a little bit further explanation. So a kinematic pair, the link of mechanism must be connected in some manner in order to transmit motion from the driver or input to the driven or follower or output. So there are different names to indicate input and output. So you can call it as a driver or input, or the driven one is called as a driven or follower or output. So the link of a mechanism must be connected in some manner in order to transmit motion. So again, within kinematic pair, we are transmitting motion from one source to the other one, actually, to the output. Sorry. The connections, the joints, the joints between the links are called kinematic pair or simply pair. That's what we have explained. So the connection where the joints or nodes are there, they are called as a kinematic pair because each joint consists of a pair of mating surfaces, two elements. One mating surface or element being a part of each of joint link. Thus, we can also define a link as the rigid connection between two or more joints. So this is a little bit of repetition, what we have discussed. So defining again the link and yeah, so I just want to make sure you understand the rigidity. So stated explicitly, the assumption of rigidity is that there can be no relative motion. So no change in distance between two arbitrarily chosen points on the same link. So that's the standard definition for the rigid part or rigidity. Basically what it says, the assumption of rigidity is that there can be no relative motion, no change in distance. So relative motion means no change in distance between two arbitrarily chosen points on the same link. That's the definition. I just wanted to make sure you just have a revision of the fundamental definition. In the relative position of the joint elements on any given link do not change no matter what loads are applied. So this is important actually. So within the link, there is no deformation. Whatever load you have been applied, at least the designing actually. So in other words, the purpose of link is to hold a constant spatial relationship between its joint elements. Yeah, so the distance between joints, what is joint? The node, which is here. So the joint, this is one joint, this is one joint. The purpose of this link is to keep constant distance between two joints. It's not going to be change no matter what load you apply. So this is the fundamental requirement of the link, right? As I said, of course, if let's say you apply a lot of load more than the design limit of the material, so there is a chance that it might end up failure, but at least the design capacity, it should not change. All right, so another thing is simplified schematic diagram, right? You have been using this in many subjects, I would say, because whenever you have a complex system to analyze, complex equipment to analyze, or even in static and dynamic, you have done some free body diagrams. So free body diagrams or simplified schematic diagram is always to simplify the problem. Why? Because it removes all other aspects which are not necessary. For example, you're analyzing some component. So the simplified version would be that which will avoid any kind of uh, requirement that are not necessary for the analysis. So I have taken some of these, most of these definitions from this book Shigley, Theory of Machine, I think. So I just included some of the parts. So if let's say you want to revisit, you can just go back again. So as a result of the assumption of rigidity, many of the intricate details of the actual part shapes are unimportant when studying the kinematics or mechanism. So because we are assuming the link is rigid. So what does it mean? I will just give you an example. So the connecting rod within internal combustion engine is not a one straight bar. It is complex shape. So it is a big end, small end, and it is certain shape. But when we are doing certain crank mechanism, we just consider connecting rod as just one link. We don't need to go to its geometry, right? So this is called a one straight line representing connecting rod for the slider crank mechanism, which was here. Yeah, so this one. So it is a simplified diagram. Okay. So now question is it okay to do that? Because we're simplifying it. Is it okay to do that? It is fine as because connecting rod has to stay rigid throughout the process or throughout the working, the design load. So as far as with the assumption of rigidity, it is constant. So that's fine then. You just make it a simplified diagram. So for this reason, it is common practice to draw a highly simplified. So you see this book has used this word highly simplified schematic diagram. So we try to make it as simple as possible. And in fact, that contain an important feature of the shape of each link. Yeah, so you just have a simplest shape, and in fact you will see that we will do a couple of those mechanism analysis, and in each case, uh, if let's say I will just give you again the same example, the actual geometry of connecting rod. What does it mean? Your system analysis is very complicated because you have to do a lot of calculations to find out how the velocity is linked, acceleration is linked, position is linked with the angle. So it is complicated. So that's why we really need to make it simplified And then it says the slider crank linkage of the internal combustion engine, for example, can be simplified for the purpose of analysis. Schematic diagram illustrated. So it's the same diagram. So you see, actually, engine is very, very complicated stuff. So it's not easy to calculate these things. But for the kinetics or kinematic pair or mechanics study, a simplified diagram would really be essential. Yeah. So that's why one of the skill you should learn from this subject is to simplify diagram of any complex shape. So you have been given any machine or mechanism and you have been asked to. So one of the thing you need to do, you have to, which is the most important or critical step, and all of your calculations depends on that particular point. That is, you have to make sure you make a simplified, as simple as possible, the diagram. So this is very good example, slider crank mechanism, which represents the engine actually. So it continues like that. So such simplified schematics are a great help. Why? Because they eliminate confusing factors that do not affect the analysis. Let me give you a very briefly example. You know, you're very well known of connecting rod shape. So we are just looking at one link, but it has a complex shape. But the complex shape is not affecting the analysis. So it's not contributing. So that's why a simplified diagram helps you to avoid any confusing factors that do not affect the analysis. So that's kind of something great actually in this analysis. So such diagrams are used extensively throughout this course. However, these schematics also have the drawback of bearing little resemblance to physical hardware. Yeah, you have seen this slider crank mechanism. I have shown you the diagram. So you see it. This is quite a little resemblance with the physical hardware, because physical hardware mean connecting rod crankshaft is a very, very complicated thing. You have certain angles and the movements required. But here we are just making. So it has very little resemblance. As a result, they may give the impression that they represent only academic construct rather than real machinery. Yeah, this is something that's feeling you could get basically as a result, that maybe what we are doing is more like a academic, not really the actual thing what you do. We should continually bear in mind that these simplified diagrams are intended to carry only the minimum necessary information so as not to confuse the issue with unimportant detail for the kinematic purpose or complexity of the true machine parts. Yeah, so there might be some feeling saying, yeah, because the engine is complex, but the slider crank mechanism is a very, very simple. So it's more like an academic or textbook type shape. But actually, it's not really the case, because we are just trying to, because we are the analysis what we are doing here, we would make it inappropriate by adding those stuff. So that's why we don't want to include any of those stuff which are unnecessary. Just imagine if, let's say, you are interested in replacing actual piston analysis during the slider crank mechanism. So it will make your life very difficult. And of course, when you are doing a lot of effort, so you might be neglecting the major goal, the scope of the study, which is basically to look at the forces and motion basically. All right. Yeah, so kinematic chain, we had very brief definition before, but this is a little bit more widely. So when several links are connected together by joints, they are said to form a kinematic chain. Yeah. So whenever more links are joined, so several links are connected together, and of course the links are always connected through joints, so they are called as a kinematic chain. Links containing only two joints are called binary link. So you see the slider crank mechanism, the this one, so slider crank mechanism, this one has two joints. One is here, one is here. So that's why this joint is called as a, sorry, this link is called as a binary link, because it can be connected with two joints. Same way, those having three joints element are called ternary links. Those having four joints elements are called quaternary link, and so on. So keep going. So we, for a link, it is not necessary to have just two joints. It could have more than that. If every link in a chain is connected to at least two other links, the chain forms one or more closed loop, and is called a closed kinematic chain. So this is a definition for closed kinematics. So basically, it's a little bit of complicated explanation, but closed kinematic chains mean is making a closed loop basically. So you have kinematic pair, or the links are joined to in such a way that it is making a closed loop. So that's why we call it as a closed kinematic chain. If not, the chain is referred as a open kinematic chain. So that's called as open kinematic. If a chain consists entirely of binary links, it's a simple closed chain. Yeah. So if it is all binary link, so there is no ternary or quaternary link. So it's a simpler. So binary link is one of the simplest link. So that's why it's called simple closed chain. So compound closed chain, however, include other than binary links and thus form more than a single closed loop. Yeah. So there might be some, and in fact, there are some examples where you will have more than one link, basically one closed loop, basically. So it's a combination of both. So it really depends on the complexity of the machine which you are analyzing. Yeah. Right. Point variable. One of the interesting thing. So when a kinematic problem is formulated, it is necessary to recognize the type of relative motion permitted in each of the joint and to assign to it a variable parameter. Yeah. So basically this is more to do with the degree of freedom, I would say. So for any kinematic problem, it is always necessary to recognize the relative motion permitted at each joint. So you have uh, joints and you have to identify what is happening on each joint, right? So this is really the important step, because each joint has a different relative motion. And so that's why it's important to identify. I will repeat again just for you. So when a kinematic problem is formulated, it is necessary to recognize the types of relative motion permitted in each of the joint and to assign to it some variable parameters for measuring or calculating the motion, right? For example, I will just go back to explain this. For example, in slider crank mechanism, we have identified. So at 2 and 3, 2 and 1, there was a turning pair. So what does it mean? There is a relative turning motion at this particular joint. So when you're doing analysis, you draw a schematic diagram. What is schematic or simplified schematic diagram? So you have links, you have joints, everything. The next step would be to identify what relative motion you have each joint. So what is relative motion at this joint, at this joint, at this joint? So you need to make or joint between 4 and 1, because it's sliding. So that's why it's called as a sliding pair basically. And then we have to assign the variable parameters for that particular joint. So there will be as many of those parameters, these parameters, as there are degrees of freedom of the joint in question. Yeah, so this is also will be translated to the degree of freedom. So degree of freedom is being used and we will use quite a lot. So those variables. So for example, at one joint, it's a relative motion. So it has 1 degree of freedom, right? Let me go back because I think it's a good example. So now it is just turning. So it does not have lateral or linear, rectilinear motion. So it is just turning. So what does this mean? It has just turning pair basically. Yeah. So just the angle is enough to explain this. So angle is a variable here basically. So thus the joint variable of a pin joint will be a single angle measured between the reference line fixed in the adjacent link. While a spheric joint will have three joint variables, all angles to specify the three dimension. I have one illustrative example for spheric joint in coming slides. You will have a better understanding when we say a spheric joint. So what it says, uh, a pin joint. So if it's connected through a pin, so it will be a single angle measured, right? So the one we have just discussed for slider crank. So that is basically a pin joint. So you just have single angle measured reference line in this adjacent link. Yeah. So this spheric joint I will show you in a while. So it has three variables. So three angles. So it can rotate in three sides on the three axes basically. All right. So kinematic pair classification. Yeah, this is quite interesting. Uh, so kinematic pairs can be classified or divided in two categories, namely higher pair and lower pair. So this is very, very broad classification. You can say it's a higher pair or lower pair, right? So lower pair, such as the pin joint, have the surface contact between the joint element, while the higher pair, such as connection between a cam and follower, to have a line or point contact. I have just made it bold. Yeah, so I made it bold for to easy to understand. So as I said, kinematic pairs can be classified in lower and higher pair. So lower pair, like a pin joint, has a surface contact. So that's the basic difference. So surface contact in lower pair, in higher pair you have line or point contact between the elemental surface. So line or point is related to higher pair, surface contact is related to lower pair. So this criteria can be misleading in some of the example, as noted in the case of needle bearing. I assume you know needle bearing or roller bearing basically. It's a type of roller bearing where you have the roller, quite thin roller. So that's sometimes it's not really a classified or well-established deviation. But most of the textbooks, they follow this lower pair and higher pair. So we should rather look for distinguished feature in the relative motion that the joint allows between the connecting links. So of course there is a classification based on surface contact or line or point contact, but we should make sure that we try to understand the relative motion at the joint quite nicely so that you can classify in your own way, because it's not necessary that you have particular point, right? All right, so this is very interesting diagram from Chigle for lower pair. So this is figure 1.2, so the first chapter, second diagram. So kinematic pairs are divided into two categories, namely higher and lower pair. So these are the examples. Just try to understand nicely. So what it says, first one, A, this one somehow is being assembled in such a way. So this can only rotate. So you just need angle to explain, right? So you just need angle. So it's just angle there to explain its motion. So it's called a revolute. This kind of joint is called as a revolute pair or lower pair, revolute pair basically. Second one is it can only go up and down within this structure. And it has one of this key as well, just to make sure it's not revolving. So you just move up and down. It's called as a prism, or sometimes it's called as a prismatic as well, right? So it's a prism pair. So you just move up and down. So this one has a 1 degree of freedom as well. So this is 1 degree of freedom, just angle. This is 1 degree of freedom, just moving up and down. And now the C part, which is screw pair. So it is one of the screw. So where when it's rotating, so it will go up and down as well. So now you understand this. Try to understand what it says. So delta theta and delta S both are linked. So you rotate, it will move. If you don't rotate, it will not move. It will not allow to move independently. So this is called screw pair. D part is called cylinder pair. So now it is more than that actually. So you have independent movement in a revolution. So you can rotate it, but at the same time it has a linear up and down movement as well. Yeah. So just imagine, so it has a 2 degree of freedom. So delta theta and delta S are required. So the next one is, yeah, so this is sphere joint, which I was talking about. So try to understand. So this is a hollow from inside, and this link has a ball at the end. So the ball is sitting within this cross section. So just imagine this theta, what does mean? It can rotate this way. It can, if let's say this is X direction, this is Y direction. So this can rotate along X direction. So it can rotate like this. Of course, it's not rotating full revolution, because here delta theta he's doing full revolution, but in this one he's not doing full revolution. So this is called a sphere. So you see we have 3 degree of freedom. So 3 different angles are required to explain such system, right? So the next is flat pair. So what is it? It is just, this one is just sitting on a flat surface. So it has delta X, delta Y, so it can move in X and Y, and of course it can rotate as well. It's freely sitting on there. So this is called as a flat pair. Then we have some of the explanation. Yeah, so same thing. So the revolute or turning pair. So this A part, is A1, this one is called as a revolute, or it can be called as a turning pair as well. So permits only relative rotation and is often referred as pin joint. You see, we have been talking about this. Pin joint is also same thing. So you see, you can call it as a revolute pair, turning pair, or you can call it as a pin joint as well. This joint has 1 degree of freedom. Let me go back. So this joint has just 1 degree of freedom. So it just rotates in one direction basically. Yeah. The next one is prism or prismatic pair, named as P, capital P, permits only relative sliding motion and therefore is often called a sliding joint. So you see, it is just sliding up and down, no rotation. So this is called as a prism or prismatic. This joint has 1 degree of freedom as well, right? So it is just 1 degree, so delta S. The next one is interesting, the screw or helical pair. The screw or helical pair, capital H, permits both rotation and sliding. So you see, you can rotate it and then it will go up and down, right? Delta S is up and down. However, it only has 1 degree of freedom. So this is interesting. So if it has 1 degree of freedom, since the rotation and sliding motions are related by the helix angle of the thread. So what does it mean? Just imagine, so because this is screw, this is like a screw jack for the cars, when you rotate it, it lifts it up. So delta S and delta theta both are linked together. So you cannot do independent movement. So Like you cannot move just delta S and keep delta theta constant. No. So both are linked. So that's why this is called as a 1 degree of freedom. So I like this example. Why? Because this gives you a better idea of degree of freedom. I know you might have seen this before, but degree of freedom sometimes is a little bit confusing when you are explaining. This is a very good example. So even though we have two parameters, but because it is just one, both are linked. So theta and S are linked together. So that's why it's called as a 1 degree of freedom. Then he explained, thus the joint variable may be chosen as either delta S or delta theta, but not both. So you can study it as a one of those one. So not both basically, because if let's say, because there is some formula where joint uh, is linked. So basically where you can drive a relation between delta S and delta theta. So if you just change delta theta, you will know that how much delta S it is there equivalent. So you cannot do both of those. Note that helical pair reduces to revolute if helix angle is made 0. So if you keep this helix angle 0, so this will become exactly like this. So it will just rotate, right? And if, of course, if I keep it 90 degree, the helix angle. So the helix angle is this angle. So if you keep helix angle 90 degree, so it will just go up and down like this prismatic ball. So that's what he explained. So thus the joint variable may be chosen as either delta. So note that the helical pair reduces to a revolute if the helix angle is made 0, and to a prism if helix angle is made 90 degree. So it really depends actually. Yeah. Okay, the next one is cylinder or cylindrical pair permits both rotation and an independent sliding motion. So this is important. So rotation and sliding motion are independent in cylinder pair. So we have the cylinder pair. So both delta S and delta theta are independent. Here they are not independent. So that's why this will be required 2 degree of freedom to analyze result. So that's why the cylinder, thus the cylinder pair has 2 degree of freedom. The sphere or globular. So this is also called globular, represented by S, capital S, is a ball and socket joint. So this is very famous joints. We have one in the car as well, ball and socket joint. It has 3 degree of freedom, sometimes taken as rotation about each of coordinate axes. So you see this one, this ball, and this is socket sitting in the socket. So it has 3 degree of freedom. And so if let's say this is X axis, this is Y axis, this is Z axis. So it is rotating along each axis. You can also explain like that. So it is rotating along X, rotating along Y, rotating along Z direction. A flat or planar pair, sometimes called as ebene pair, which is German word actually, represented as F, is seldom found in mechanism. So it is not really common actually uh, in its disguised form except at sport point. So it is basically a sport basically. It has 3 degree of freedom, that is 2 translational and 1 rotational. So 2 translational and one this one and 1 angular. You know, this is more like a sport of any. For example, you have a table sitting on a flat surface. So the base of the table or leg of the table can do these 3 movements. So you can do X, Y, and you have angle as well. So this will be one of the examples. So it's not really quite common for engineering analysis, but it is actually classified. All right, so these are all lower pairs, right? Where you have surface contact. I will repeat again. Make sure you understand. So lower pair has a surface contact, right? So these are all classification where you have surface contact. You see the surface to surface contact is there. So now all other joints types are called higher pair. Any other joint which you classify will be called as a higher pair. Examples include, for example, gear teeth, So gear, when they are meshing each other, so they have kind of like line contact. A wheel rolling, sliding on a rail, so this is also a line contact. A ball rolling on a flat surface, this is like point contact. And a cam rotating its forward, contacting its forward, so it's also like a point contact. Since an unlimited variety of higher pair exist, a systematic accounting of them is not realistic objective. Yeah, so that's why it is not nice to classify higher pairs. So that's why just the lower pair are being classified, that's fine, and we will do the analysis. And for higher pair, since because it's unlimited variety is available, so a systematic counting is not available. Among the higher pairs is a subcategory known as wrapping pair. So one of another example of the higher pair is the basically wrapping pair. What is wrapping? So examples are the connection between belt and pulley. I'm quite sure you have seen belt and pulley. So pulley and belt, so it's wrapping around the pulley, so that's why it's called. Or a chain and a sprocket. So in a bike, normally you have this combination, or even in the timing chain when you say in a cars. So in a simpler word, you can say chain garage jo set hota hai. So chain and sprocket, or a rope and drum. So rope is being gone out of wrapping around the drum. So this is another example. In each case, one of the link has only one way rigidity. So we will still consider as a rigid part, but it would require some further attention. So the message here, uh, classified as a lower pair and higher pair. Lower pair is a part where you have uh, surface contact. Higher pair where you have line or point contact. There are many examples actually where you can have higher pair, so that's why they're not classic. One of the category being explained as a wrapping pair for belts and pulley and chain and sprocket, for example. And most of our studies would include some analysis using lower pair. So that's why that's why the classification has been provided. Not only in this book, in books, because lower pairs are, so that's why we need their understanding, a good understanding. Now everything is summarized in one of the table from the same book, which I would really appreciate if you try to remember it actually, or at least you know very well actually. So these are the pairs, lower pair we have seen. So revolute, prism, screw, cylinder, sphere, flat, and the nomenclature as well, because when we are doing analysis or problems, we write this particular nomenclature. And the variable, you need to know that what variable is. So revolute, you need just one variable, that is delta theta. For prismatic or prism, P is a symbol and we write delta S, and because it's a one parameter, so it's a 1 degree of freedom, and the relative motion is rectilinear. Then we have a screw where you have a H, so it has delta theta or delta S, not and. Just make sure you understand. I have explained. So delta theta or delta S, so it also has 1 degree of freedom. It is called as a helical. Then we have cylinder, which is C, so delta theta and delta S. So two variables, so we need 2 degree of freedom. Then we have a sphere, which is capital S, so delta theta, delta phi, and psi, basically 3 angles, right? So that's why it has 3 degree of freedom. Then a flat, relatively less common combination, so delta x, delta y, delta theta, so it's a planar. So it has 3 degree of freedom as well. So you see pair variables are also linked to the degree of freedom. So you have degree of freedom and pair. So, but you need to make sure that, for example, these are very good example. Here you have delta theta and double delta S because both are independent. So that's why it says 2 degree of freedom. But here you just need one of those. So delta theta or delta S. So you have just 1 degree of freedom. All right.